Hi everyone, my name is Norbert. I'm leading the product side at ZkCloud. We've recently rebranded to ZkCloud from Gevulot. Actually, Gevulot is the lab entity building ZkCloud, just in case that's a more familiar name. And today I want to talk about a little bit and give an intro about Firestarter, which is the permissioned version of our mainnet, and and give you a practical guide how to generate proofs on Firestarter. It's kind of like reshaping the proving infrastructure space, both from the cost perspective, also from the decentralization and performance perspective. But let's dive in. So a couple of things first about our core principles. At Gevulot, we believe that ZK proving should be fast, cheap, and truly decentralized, and that's the vision that we've been building ZkCloud with. So whenever we designed the protocol, we actually focused on decisions that are in favor of decentralization, that touches down to, for example, prover node selection, et cetera, et cetera. So we wanted to avoid everything that could lead to centralization, bring about liveness risks, censorship risks, et cetera, et cetera. So basically, we've been building the network along these values. Now, what is ZkCloud? So basically, ZkCloud is the first universal proving infra for ZK. That means, like in 3 words, it's really fast, cheap, and decentralized. It's a highly optimized compute network. So it's fast, it's cheap because we are aggregating workloads from all over the industry and drastically reducing the costs for participants and reaching for users and reaching pretty high hardware utilization for our node operators. And also it's decentralized because from the early days, we've seen that proving is very susceptible to centralization being a very compute heavy task. And we didn't want to recreate the situation in Web 2 where there are a handful of large operators or cloud providers providing that compute to the industry. So a quick overview of our architecture. So there is a universal proving layer, an orchestration layer, and then the compute layer. The proving layer is universal because we support any proof system. And this is one of the key elements, how we can actually aggregate workloads from across the industry. There are flexible ways to interact with our network or integrate with our network. You can use our pre-deployed provers and generate proofs for those, or you can deploy your own prover as well. I'll go into more details on a couple of slides later on these. And we've got an orchestration layer. It's a blockchain-based mechanism, so we've got a very minimal L1, a Cosmos-based L1 underneath that's managing workload allocation. It's managing reward distribution and economics. And this orchestration basically it works on the node level and at the network level as well, meaning that we've got pretty powerful nodes, you'll see it on later slides, that can process multiple proofs, absolutely independent ones parallel, or we can orchestrate among multiple nodes if there is like a very heavy workload that needs, 10, 20, or even more prover nodes to work on, and then the proofs to be aggregated. And this is also, it contributes to our optimized hardware utilization. And the orchestration layer also includes these execution guarantees that I'm going to talk about a little bit later. It's very important, I think, to mention execution guarantees because there are a bunch of prover networks out there. But for example, when it comes to prover selection or workload distribution, most of them simply just go with an auction, and they basically externalize the entire problem of economics and let the market decide the cost of proving. The user picks a bid, and off they go. However, it's very hard to build in any execution guarantees for an auction, because if there is a non-delivery of the proof, you simply need to restart the auction from all over. And then you end up having latency issues, you may end up having finality issues, you may need to prune the chain, et cetera, and then face reorgs in case there is too much latency there. We've taken a very different approach through random selection, which is a more natural and more credibly neutral approach relevant for blockchains. And then on top of random selection, we can build in a bunch of execution guarantees to make sure that without any additional action, the user is getting served the proof for their request. And we have a decentralized compute network underneath. GPU, CPU workloads are or can be processed by our network. But just yesterday, we attended the Fabric event, who are building the custom silicon specifically for ZK computation. And we are looking to work with them to integrate them in the network as well. So yeah, let's move on to Firestarter. Basically, Firestarter is the name of our network up and running now. It's the end-to-end implementation of our ZkCloud mainnet, just running in a permissioned way. It means that we run all the validators for that minimal Cosmos chain. By the way, the Cosmos chain is indeed minimal. We don't host smart contract state, etc. So it's purely for managing workload distribution and reward distribution, basically. We run all the validators now, but with the upcoming mainnet in a month or two, we are looking to decentralize that as well. Proving is already decentralized. Yeah, and it's a scalable production-grade network. We've got a few available provers now, some big names, RISC-0, SP1. We are closely working with the ETHDenver team, the Polygon ZK EVM, ZkSync, etc. Some of them are already there, some of them are coming very soon. We had a DevNet running where most of these were integrated, and we need to move them all over to Firestarter. And basically this network, to be able to scale and to be production ready, it has been rebuilt from scratch. And you'll see that a little bit later as well. I mean, currently I'm not talking about our DevNet, but we were using Nanos VM, and the provers were running in a Nanos VM on the DevNet, but it seemed to be just too painful to use this additional tooling for the developers. So we basically switched to containers, and containers are running in a Linux VM. It's very familiar tooling for any developer. You can customize the resources that you want to be added to your proving job. I'm going to talk about that a little bit as well. And as I mentioned, it's a network ideal for large workloads where you need to parallelize basically, for example, the segment proving of RISC-0, where the segments are generated, in parallel and then aggregated over a multi-level aggregation tree, or STEX proof tree construction also is something that we've been integrating. Yeah, Firestarter is an incentivized network, by the way. I mean, anyone can join in now as a prover node if they want to contribute compute. But yes, the workload allocation. So we've got random selection among the nodes who have free capacity in the network. It's important because, as in any other blockchains, this is the most neutral method to avoid centralization. Obviously, I often get the question, but what if someone runs a bunch of prover nodes on our network? Then they have actually more probability to be selected. Yes, that's true, but that's the characteristic of any blockchain if an entity is running multiple validators. Like just for being selected for block building, if you run multiple validators, then your chances of being selected is simply higher. So it's not specific to us, it's specific to random selection. Yep, so our consensus is Comet BFT based, and we've got fallback mechanisms, automatic reallocation, and if the secondary prover doesn't deliver, we open it up for a race. Anyone can come in and deliver the proof. So it's like a multi-layered execution or multi-layered fallback mechanism where we've got a primary prover, a secondary prover, and then an open race for anyone to come in. Yes, so proving on Firestarter. It's live now. You can try it now. We have a tool called Gevulot Control to interact with the network. You need to generate an account. And yeah, in our docs.gevulot.com, yeah, as I mentioned, Gevulot, this one here used to be our initial name, but ZkCloud is the product we are building at Gevulot. The docs are still under the previous domain. So you can find more information here. Obviously, you'll get your address and the secret mnemonic key. You can purchase credits. 1 credit is $1 to start proving on Firestarter. You will see that if you throw in $10, you'll be fine for quite a while proving, because we are making proving super cheap. So it's not, people were asking, like, do you have a free tier? And we were saying, well, it's so cheap that it doesn't really make a sense to make a free tier. You throw in $10 and off you go. So we don't, but you'll see. You can use USDC or credit card, whatever, and then you can spend your credits according to your usage. So you define the number of CPU cores, RAM, and the amount of GPUs you want to be allocated to your job. And you also tell us, on this program with this input and those resources allocated, how much time does it take to generate the proof, or for how much time should we run the program. And then you pay for proportionally for the time and for the resources that you've been using. So any program that compiles into a Linux binary can be deployed on Firestarter as a prover. I also have to say that when you deploy a prover, you also need to deploy the corresponding verifier program, because, like, for example, even though you may settle your proof on Ethereum, so you don't care about the verification done on Gevulot or on ZkCloud, sorry, we still need to be able to verify your proof in our network, because based on that can we only pay our prover nodes the rewards. We need to know that they generated a valid proof, and then we settle the rewards with them. And then any program that can run in a container can be run on Firestarter. So basically, we convert container images into a Linux-based VM image, and that's how you deploy the provers on Gevulot. There are a couple of prerequisites, but nothing special. We've talked about the Gevulot control already. And then either you have a pre-built container image or you have a working container file. You can very easily convert those into a VM image and start generating proofs. Now, how do tasks look like on Gevulot? Every task includes the URL to the program, or if we already have that program deployed on the network, then you can use the CID of the program image. We have an internal IPF, a private IPFS network, so your program will be pinned to a bunch of prover nodes. The rest can download it from multiple nodes very fast, and so you can reference the URL of your program or the CID in our private IPFS to your program, and then the command, program arguments, input-output files. Then you need to include hardware resources and the compute time. So tasks can be submitted simply through the Gevulot control. You see the command there. It will output, it will have this transaction output and tell you the status also. And then fetching the task details, the status, or fetching the proof is also working through the Gevulot control tool. It's very simple. So basically, if you look at the task file, the YAML file on the right, you see that basically it references the image from a publicly available domain, and then you define the input source, also in this case from a publicly available domain. You define the output contexts where we should save the proof, and the retention period, how long we should keep your proof in our IPFS network available for you to download. That's in seconds. And then you also need to define the resources. Like, this is a simple hello task. So basically, it's one CPU core, 512 megabytes of RAM, so it's ½ gigabyte, and 2 minutes of running time. But yes, so this is how it looks like when you are preparing for task submission. A little bit about the pricing and also the specifications that our nodes have. I think it's important. 2 key things. It's a pay-as-you-go pricing model. So currently people are burning a bunch of money on idle time, renting servers and using them only when they need it. Forget paying for that. It's pay as you go based on your usage and the time you use the resources for. You see our GPU nodes both have two 4090s each, 400 gigs of RAM and 64 physical cores. And this costs 84 cents an hour if you were submitting a workload where you want the full capacity of this node and you want it to run for a full hour. That actually translates to $600 a month, which is super cheap for two 4090s for a month. But obviously you are not renting for a month. You are just paying for whatever you use for your actual task. It's just more expressive if we say, okay, what does it translate to in a monthly figure? And then our CPU nodes have 96 cores and almost 800 gigs of RAM. It's 60 cents per hour, 61 cents per hour, and that translates to $440 per month. So basically, we needed this also to be able to parallelize workloads within the nodes. Because, for example, a Polygon ZK EVM prover needs the full capacity of this CPU node, but most of the other provers don't. So in that case, we can actually further amortize the cost of proving. And besides making proving decentralized or offering a decentralized alternative to the centralized providers, the other core goal was to make proving like an order of magnitude cheaper, at least, than what it is now. That's how we basically designed our economics, baked it into the protocol. Because again, like if you have an auction and then there are some really powerful entities gaining dominance there, they can start controlling the cost of proving over time. Now, if you design a network, like if you design economics within your network and bake it into the protocol, you pair it up with random selection and fallback mechanisms, you have a pretty robust network where people cannot mess up what you have built. Two quick examples. A GPU workload where instead of two, you only need one GPU, 32 cores and 200 gigs of RAM, and your program runs only for 5 minutes, then you pay 3.5 cents. Or a CPU workload where you run it for 10 minutes, you need half of the 48 cores and 400 gigs, it's 5 cents then. So yeah, basically that's how it works. The network is open for anyone to come in and join with, contribute with compute capacity. They need to meet the minimum requirements of the different node types, because we have to ensure that there is a standard quality, like high quality hardware level in the network. Yep, and with our Firestarter network, it's, as I mentioned, it's incentivized, so you can be an early contributor. Yes, so basically we are launching our permissionless mainnet in about a month's time. We are coming out with the detailed economics for mainnet very soon, but you see these numbers that I have shown, they are not going to change. So these are the ones baked into the protocol, and we are publishing the rest of the details very soon. I mean, many of the things are already in our docs. If you are curious, feel free to go in there. And yes, ZkCloud.com includes everything, our socials, our link to our docs, our GitHub. Feel free to play around if you have a use case that needs proofs. Yep. Thank you very much. Yeah, happy to answer any questions if you guys have.
So maybe I can start.
Yeah.
So I think you're basically pricing in terms of the time, right? So the
compute time and the resources.
But I think compute time is, I mean, for a node in your network, the compute time they can decide the compute time. I mean, how did you know the compute time? You can report a false compute time, right?
Yeah.
If they're dishonest.
Yes, absolutely. So there are two things there. It's a very valid point. So on the one side, since we are making the network absolutely universal, so anyone can bring their own prover binary, deploy it, and send proofs, most of the binaries running on the network, we won't have any information about those. So it has to be kind of the task of defining how long we should run that binary has to be with the user. So whoever is requesting the task, since it can very well happen that we have no information of that prover program, they need to tell us how long it should be running. On the other hand, the way we protect our nodes from being punished in case someone maliciously puts in, an irrationally small compute time, so it's not possible simply to complete the job within that period of time. What we do is we have the secondary thing. So the fallback mechanism helps there. So the initial prover starts running it. The user put in a maliciously small proving time. The first prover will not be able to complete the job. Then whether we punish this or not depends on whether the second prover will be able to complete it. So we throw the same job to the secondary one in the fallback mechanism. If they can complete it, we know that the malicious act was not at the user side, but our prover nodes didn't do the job. If the second one cannot complete it either, then we know that the user messed up something because the program is not possible to be completed within that period of time. So basically, that's how and in the first scenario, where the second one successfully completes the job, we will punish the first prover. In the second scenario, where none of them can complete the job, we won't punish any of them because we know that there must have been some issue at the submission level which we cannot really influence, or we don't have any view on that because any user is free to bring any prover program and submit any task related to that. But it's a tricky thing from a mechanism design perspective. Actually, you pointed that thing out very rightly, to design everything in a way that we are covered for these scenarios and we don't unnecessarily kick out our provers from the network, or we don't punish them unnecessarily. Yeah.
How much do they need to stake to become a prover?
It's a very interesting topic because I cannot share too many details at this moment because we've been rethinking that and we will publish it with the mainnet docs coming in a couple of weeks' time. But the economic security behind proof generation is something that has not really been researched a lot. Everybody is just going with the default thing, okay, you need to throw in a bunch of stake. Now the interesting thing with proving is that it's somewhere between proof of stake and proof of work. For proof of work, basically it's the hardware commitment, your uptime, your operational costs, etc., that is there. Plus, and in that sense, proof generation is a very similar task. We could even call it proof mining, where you need, like, to build these types of machines, you need to throw in 15, 20K initially. I mean, you may be able to rent some of these from providers, but the thing is, again, to be able to bring down the cost of proving a lot, so to make proving cheap for the user, there is a certain limit up to which we can pay rewards for our prover nodes. Obviously, there is an incentive, a network incentive between the two, but a prover node operator will never gonna be profitable on ZkCloud if they just rent a server on AWS or GCP, because it's just too costly. We want people to go back to on-prem machines or rent from data centers, run their own machines, because in that case, they will be absolutely profitable on ZkCloud. But we also, want to avoid a situation where we build a decentralized network. It looks nice, but at the end of the day, 95% of our prover node operators is just renting on Google Cloud. And then what did we, we messed up our entire design just by that. So we had to think about it from different perspectives. And coming back to economic security, so you buy that machine or rent that machine, you cover the operational costs, then we have to balance the entry barrier. If people need to throw in a couple tens of thousands of dollars of stake on top of buying these machines, that increases the entry level a whole lot. So we've been thinking a lot about reputation systems. Actually, we recently published the State of Proving Infra report, and a certain section of that is actually about economic security. You could use reputation systems. You could use constant capacity and availability verification of nodes to prevent Sibils, for example, 5 people registering and using one machine only. So if we throw them in a lot of tasks to complete, like test tasks to complete and prove capacity, then you could actually prevent them to stay in the network too long. So there are a couple of things. Also, reputation-based rewarding, for example. You earn your reputation, and based on that, your rewards increase as well. So there could be a couple of things that you combine, and you could even leave staking out because already the economic commitment for the hardware and the additional other elements there could basically make up for most of the purposes that staking serves in other, I don't know, POS networks where validators just need to stake because there is no other option to make sure they are honestly behaving. Yeah, so we tried to rethink that, and we'll publish the actual docs in a couple of weeks' time. But yeah, that's an interesting question, and we are looking to do more research on that to see what's the best setup, because it's not a POS validator where you don't need too much hardware. It's not a Bitcoin miner where there is no stake at all involved. You need to balance somewhere in between the two. You need to balance in a way that there is no wasted compute. That's also a tricky thing, because wasted compute on Bitcoin is part of the consensus and the security of the network. Like everybody racing and only one getting rewarded. You cannot do that in proof generation, because if there is a lot of wasted compute, proving is never going to be cheap. At the end of the day, someone has to pay for that compute, you know. So yeah, it's an interesting matrix to think about, but I think we managed to design a very robust and powerful system. But I'm looking to have any feedback. If you go to the docs or read our article about economic security, if you have any feedback, we are really open to that. Yeah, thanks. Thank you for having me.